today I want to look at plotting power functions and using these laws of indices, really the laws of logarithms, but they come from the laws of indices, to actually arrive at a function that describes two variables. And that's what we're going to be doing using this autograph software today. So here's a reminder of these laws of indices. So long as the base is the same, remember, I can add the powers when I multiply them. I can subtract the powers when I divide, and so on. There are 6 of these things, and last time we looked at how they arrived at. From these come the laws of logarithms. A logarithm is a power. So the logarithm of a number is the power to which 10 is raised to give that number that we looked at last week. So because I've turned them into powers, then when I multiply two numbers together, if I turn them into powers, I add the powers. If I divide, I subtract the powers, so I subtract the logarithms. And the key one that we're going to be focusing on is this one, which is really useful, because if I want to find out what n is, if I find the logarithm and turn it into a power, then that n can come down and become a multiplication, which means I can then find it using algebraic manipulation that we've been playing around with. So let's have a look at an example of how that works. Plotting power functions. If you've got the textbook here for the maths, it's on page 277. If you've got the old version of the textbook, it's around about there. Power functions. It's work problem 2. Just pause while you... So what we're going to do with this is we're going to try and prove that this relationship is true. That the power is related to the current with that relationship, Ri to the n. And actually you may know the formula that relates power and current for a circuit is what? Voltage times current. But what is it to do with the current and resistance? Anyone know? I squared R, right. So actually we're going to prove this law. So we should end up with n equal to 2, and the value we get for R in this little set of results we've got here will end up giving us the resistance of the circuit. So it's a power function. It is the assumption we make. A power function means that one of the variables, in this case the current, is related to the power with some, related to the power via some other power, some index. Okay, and we want to try and find out what they are. And we use logarithms to do it. So assuming power equals Ri to the n, we use logarithms to expand this. Yeah. Am I not? I hope I am. Yeah. Okay? So, we use the laws of logarithm to expand this function. And as we were doing last week, for solving indicial equations, we find the logarithm of both sides. The whole point is to try and get this power down to become a multiplier. So we find the logarithm of both sides, like we were doing last week. So we take our power equals Ri to the n. And we take the logarithm of both sides. Now we have the logarithm of two things multiplied together, r and I to the n. So that multiplication becomes an addition using the laws of logarithms. Using this first law of logarithms, log of a times b equals the log of a plus the log of b. So we can rewrite this as, therefore, log p equals the log of r plus log of I to the n. And then we recognize that from the third law of logarithms, if I've got the logarithm of a to the n, this becomes n times log a. So finally, I can write this as, therefore, the logarithm of p equals the logarithm of r plus n times the logarithm of I. And it's important to recognize that this is the same as p equals r I to the n. This is the same function, p equals r I to the n, but written in a different way. We use logarithms of both sides so that we can then split this up into its constituent parts effectively using the laws of logarithms, but that is the same as that. What we're saying now, though, is that instead of power being related to current directly with some power n, so if I plotted a graph of that, it's very unlikely I would get a straight line because I is to some power that we're going to try and find. We've now turned that into a relationship where if I were to plot not power, but the log of the power against not the current, but the log of the current, then there's no power associated with the log of I, so therefore I should get a straight line. And that, as soon as I get a straight line in the graph, that means I can say all sorts of things about it. So let's just quickly review straight line graphs. If I just make the note, the equation of a line, which is something that you've all done at some point in your school careers. It's a classic GCSE topic. If I plot two functions, y against x, and I get a straight line, then I can write down, or I can find the equation of the line. And the equation of the line is y equals mx plus c. Hopefully that rings a few bells. And you're going to tell me what m represents. The gradient. Where m is the gradient of the line. Y over x. So what I do is I just draw a triangle at any convenient point on the line, a right angle triangle, and divide y by x, and the gradient is whatever y is divided by x from the scale, measured from the scale. What does c represent? What in particular? The y-intercepts, right, yep. Okay, so C is the y-intercept, where it cuts the y-axis. And that makes sense because that's the point at which x is 0. And if you note in this equation of the line here, when x is 0, this bit disappears, and so I'm just left with y equals c. So how do I find c? It's wherever it cuts the y-axis. So c is the y-intercept. Now if we look again at the power function that we came up with, at our power function written in logarithmic form, I'm going to write it in a slightly different form. Log p equals n log I. I'm just going to put that bit first, plus the log of r. Then we can see, if we compare that with we can see direct relationship between the two. If I plot on the y-axis log of p, and on the x-axis log of I, then the gradient will give me the value of n, and the y-intercept will give me the value of log of r, from which I can find r. So to recap this thing then, because it's quite an important process that we can use a lot in science and engineering, I've got two sets of results. If I've got two variables that I'm plotting, I plot one on the x-axis, one on the y. Usually the one that I'm controlling would go on the x-axis, and the one that I want to observe goes on the y-axis. So in this case, we're going to put the current on the x-axis and plot power on the y. I'm looking for the relationship. What is the relationship between these two variables? If I get a graph, I might get a graph that looks, I plot y against x, I might get a curve. Well, that tells me there's some sort of relationship. I might get a curve like this. I might get a straight line if I plot it. I might get all sorts of things. If I get random dots all over the place, then I say to myself, there's no relationship between these two things. But if I get a curve or a straight line, there is a relationship. What I'm after is, what is this relationship? And this is a classic way of finding out what that is. Don't guess. Assume, you might say that's the same as guessing, assume that it's this relationship, and then what we do is we use the laws of logarithms to work out what that relationship is in another form, in a logarithmic form, and then we see that it looks like I ought to be getting a straight line if I'm right. If I'm right and the relationship is power equals Ri to the n, then I should get a straight line. That said this. So if I plot it and I don't get a straight line, then it's not p equals Ri to the n relationship. I've looked somewhere else. But if it is a straight line, then I'm correct in my assumptions. It's some sort of power function. And more than that, I can find out what these constants are in this relationship. So if we compare that finally with p equals Ri to the n, I can then go back to that original function and I can calculate r and n, because n is just the gradient of the line, if I've plotted it, and the log of c, sorry, that c gives me the log of r, so therefore r turns out to be 10 to the power whatever c is, because that's the inverse of the logarithmic function, or the logarithmic value. And that's what I want you to do with this set of results. I want you to find out what the log of I is and what the log of p is and plot that on autograph. So before we go down there, I want to just show you how autograph works. So I'm going to